Let's continue to look at the examples here in these sections. We're going to exercise with numbers to see how can we calculate the shear stress. Here probably you still remember the key step in determining the shear stress is in the calculation of the Q. The Q is for shaded area, and once you select the level at which you're interested in determining the shear stress, shear flow, or shear force, for example here, then the shaded area can be either the area in the cross section above the level you select or below. So either option will allow you to determine the value of the Q, and either option will reach to the same magnitude of the Q, but they simply is opposite in sign. Okay, and so that is for the Q, and then for the tau equal to VQ over IT. Then how do we determine V? V basically most of the time is to obtain through the plotting of the shear diagram. Okay, that is I prefer it because shear diagram can provide you all the information throughout the beam from here to here. For example, if we are interested in this section here, then basically here is the P. And from your experience of building up the shear diagram, you can see the shear diagram, the curve there wouldn't be just like this simple. They can be changing, can be other various forms. So basically, build up the shear diagram will be convenient for determining V here. And what is T? T basically is the here is the level you selected, and then here this is the width of the level in the cross section. So that's T here. Okay. And I is the moment of inertia respect to the whole of the moment of inertia of the entire cross section respect to the neutral axis. So keep this in mind. And then here we have a shear flow VQ over I and shear stress. Basically, we're going to exercise the two equations. And before we proceed to the more quantitative examples here, then I want to kind of give you kind of schematic, give you some kind of scenarios for better, how to say, provide you the better skills in the dealing with the Q, this value here. So, for example, if we are interested in determining the shear stress at this level, okay, and then here you have two options. If you choose the option 1, which means you choose the shaded area above this level and come up with this kind of short T shape. So basically this T shape, how to calculate Q, we know the Q equal to the, for example, let me say this shaded area is A star, and then from the centroid of that shaded area to here is the Y bar start, and we know the Q is determined by these multiplications. And actually in practice you can determine Q by doing this. Q equal to Q1 plus Q2. You simply, for this one, you decompose two simple easy shape. Okay, for example here I decompose one here, another one is this one here. You decompose into two simple shapes, and for each one you can easily determine their centroid. And for example here, let me call this as the Y1 start bar, okay, and this one is the A1 start. So Q1 equal to A1 start, Y1 start bar. In the similar fashion, this one let me call the A2 start, and this one is Y2 start bar. So basically Q2 equal to A2 start and Y2 start. Okay, so under this kind of decomposition into the simple shape, that will allow you to easily determine the location of the centroid and easily calculate the area, and then you simply added up the two things together. So this is the kind of the tip you can carry on. On the other side, you have another option to choose the shaded area, which means Again, this is the level you are interested, so why not you pick the lower portion as the shaded area for yourself to determine the Q. And then the Q determined by the second option will be the same value as we determined from the upper option here. Okay, so keep the kind of things in mind. Then again, we revisit the slides, and here we're interested in knowing majority is the where the maximum shear stress is. Okay, that is the most interested items we're looking for. And here, when the beam has no shear stress, okay, so basically the shear stress I can tell you in the upper surface. For example, if this is our cross section here, okay, and this is our neutral axis. And for example, if this is the transverse loading here, okay, that's a V here, and here I'm going to tell you the shear stress happen at the top and bottom surface. So here is the tau equal to 0 here, tau equal to 0 here. Okay, and do you know why? Because for this case, when you choose the Q, then basically you can find the Q equal to 0. So that's the reason why on the top and bottom surface, and that parallel to the neutral axis, the tau equal to 0. Okay, so basically once we explain this one, then this should be easily answered, and just like this. So now in the remaining we will focus our exercise on the second one, and how to determine where the maximum shear stress is. Okay, that would depends on the shape. So for example, here we look at the rectangular cross section. So this is the rectangular cross sections. Okay, rectangular cross sections section. Okay, the beam in 3 dimensions you can visualize like this. Okay, so the beam is something like this one. So from here we can see we can first exercise. For example, here let us pick the level at which we're interested in determining the Q, the tau. Okay, so from here tau equal to VQ over IT here. So from here we can individually determine, for example, the V is the transverse loading, and that one suppose we are knowing. Okay, so something like this one, and this one you can obtain by shear force diagram. Okay, and what is Q? Q, for example, here let me pick out the upper shaded area in the upper portion there. So Q can be equal to the area. What is the area? Area equal to B, and multiply with this one. Okay, so this one is equal to C minus Y. Okay, and then multiply with from here to here, that is a Y bar. And so what is Y bar? So let me do the little bit multiplication here. So that is B times C minus Y, and Y bar basically is the average of this quantity and this quantity. Okay, so that is 2 and Y plus C. Okay, so basically here the Q you can determine is 2B and then C square minus Y square here. Okay, and I is a moment of inertia of the entire cross section respect to the neutral axis, and which is this one, the Z axis. So that is 112, and B times the dimension 2C cube. Okay, so that one let me simplify. So that is 8 12 BC cube. Okay, so that is 23 BC cube. Okay, and what is T? T is the width here, so that T equal to B here. Okay, so we plug in everything here. So in this case, that is V times B over 2 and times C minus square, C square minus square, and I is 2 over 3 and BC cube, and times T equal to B here. Okay, so by doing this, and we can try simplify the things. And so let me change color. So let me first deal with the this one. Now becomes 3/4 here. Okay, and then let me cancel the b here, and then basically that becomes is bc3 and v and c square minus y square. Okay, and then here let me try to get into this form. So basically let me divide the numerator and denominator by c squared. So that is 3 4 v b c, and this is the 1 minus y squared c squared, something like this one here. Okay, so we're almost done. And what is bc? If you back to this one here, the cross sections has the area. Okay, this area equal to, look at this dimension, is b times 2c. Okay, so basically b times 2c, basically here is 3 2v, b times 2c, and 1 minus y squared c squared. I'm out of the space, let me move to here. So basically, therefore tau equal to 3/2 and v and a, okay, and 1 minus y squared c squared here. So after simplification by this one, we have this equation here. From here you can see basically the tau xy as the functions of the, let me erase unnecessary information here. So you pick the level at which you're interested in knowing the tau, and this level is the let me designate that is a position y here. So basically this tau xy you calculated is the y is a function of y. Okay, so that is the function of y here. Okay, so that's a function of y. So the maximum value for this case definitely is when 1 minus something, this minus term becomes 0 when y equal to 0. So basically the maximum occur here. Okay, this is where the tau maximum occurred. So the maximum shear stress occurred at the middle along the neutral axis for rectangular beams. Okay, the direction, again, the direction of the shear stress is like this. Okay, so here that at any level, the direction of the shear stress is like this. So for this case, this is the component. This shear stress is in the x-plane because this plane has the out of normal in x direction and pointing to y direction. So that reason why here we designate that is tau xy. Let's take a look at the shear stress in standard beams. This is the I-beam. This is kind of industry standard beam, and usually they designate as the S-beam or W-beam. Those kind of the terms you can refer to Appendix C. Okay, from there they have tabulated many kinds of this kind of standard beam here. Okay, so to determine the average shear stress, we're still using this formula here. Okay, so for example here, if you would like interested in determining the shear stress along this level, along the BB, then you pick up this formula, and then this, for example, you can pick up this as your shaded area. Okay, and then again for this shaded area, you can utilize this this technique on this page to help yourself. And the maximum shear stress, and basically you can again apply the concept, and the shear stress will be here, happen here at the middle here, because that is where for tau equal to VQ over IT, whenever we want to find the maximum, then basically we try to maximize this kind of parametric term here. In this term, V is constant, I is constant. So the two you wouldn't be able to change whenever a cross section is selected. However, from here, if you want to maximize the shear stress, you can find a place where the maximum Q will be occurred at the same time. The T minimum would occur at the same place. Okay, so for this case, they just happen at the same location, CC prime, along this cross section here, where the QX maximum, T is minimum. Okay, and most of the time we can approximate the calculation of the shear stress by this formula. You simply divide the V by the area of the web. The area of the web is this area here. So this is the area of the web area. Okay, so this one is provided as approximations, and this approximation seems reasonably good, so why not we take it? And if you want to be critical and then be precise, then you simply back to here using these general equations and do detailed calculation. Then you should get a very precise calculation of the shear stress anywhere, including at BB here. Okay. Before we look at the examples here in these slides, I'm going to, again, I raise up a few scenarios, and again to reinforce your understanding of the Q. So the first one, we look at the this case and compare to this case here. So for this case, we choose the shaded area is like the green one, the dark green one here, compared to this one. And the shaded area for this case, let me call this is Q2 here. So compared to the Q1, of course, Q2 greater than Q1 here. Okay. And then we compare, right now the next one, we compare this case with this case. Okay. So for this case, you can see compared to the Q2 here, the Q2 corresponding the shape is up to here. Okay. And now for Q3, if you decompose the Q3, if you like to decompose, Q3 can be decomposed into this, and which is Q2 plus this. Okay, let me call the Q, whatever, let me call say Q, QA, how about that? Okay, so QA. Okay, so for this case, you can see the QA, when you do the calculation, QA has the centroid is here. For this centroid is negative, okay, because it is below the neutral axis. So this, when you do the calculation, the area, whatever the area of this, and multiply a negative y bar here, negative y bar here. So basically here, this is a negative. So compared to the Q3 and Q2, from here you can see Q3 because equal to Q2 minus something. So basically here we have Q2 greater than Q3 as well. Okay. So that is the second scenario. The third one, the maximum basically happen is just like this, and that just happened when you select the sections, the level you're interested along the neutral axis. Then the shaded area either above or below that will give you the maximum value of the Q. Okay, so that is the three scenarios, and here provided. So we can look at this the more practical example here. So we are given this kind of beam and under three different individual point loading. So here we are given the allowable normal stress and allowable shear stress. We want to determine the D here. So which means we want to determine the dimensions of the beam AB, and such that to meet the two things. So for this case, this one will be, we need to draw is, you can expect this beam will have the shear force and also will have the bending. So from bending, we know the bending will induce is my over I. This is the magnitude, and that will cause the bending stress, normal stress. And this also will have the shear force, transverse loading. So we from the V, and we will induce VQ over IT, and that give us tau. Okay, So that is the tau, and from here this one must be less than or equal to the allowable. Okay, this one must be less than allowable. So that is our design, the kind of the calculation procedures. So we simply need to dig out the information and make satisfied with this one. Okay, so basically this one we will exercise. So in a way, because we know we want to determine the my over I for bending stress and tau equal to Vq over IT for shearing stress. So the first step we need to determine is the V and M, okay, and then we're interested in maximum because we want to have that one is allowable, less than allowable, okay. So in this case, we want to find is the maximum, and the easiest way to find the maximum of this value is by drawing the shear and bending moment diagram. And again, this is the typical exercise from chapter 5 here. So we just leave the detail to you to figure out. Okay. So from here, you can easily see the maximum shearing stress has a magnitude 3,000 pounds. And the maximum bending is 7.5, this value here. Okay, so 90,000 pounds each. Okay, so we keep these things, we move on here. So now for our case, the first one we check against the normal stress criteria. We need to satisfy this one, and we are given is this one. So here we simply plug in. So now from here for this one, we're simply using this stress equal to my over I in terms of a magnitude, and then that one we also can be in terms of the S here, and that is our textbook solution, but here we can exercise here. So from here you can see this is our neutral axis. Okay, so again, if you wouldn't be still confusing why the neutral axis is like this, and again back to the chapter 4. But here for this case, I can maybe a little bit more detail. If you look at the 3D, the beam in 3D like this, and now the bending is like this way. So basically this is the neutral axis, okay? So from this case, let me plug in using this formula here, and rather than this one, let me use this one. So now for this case, the bending equal to we given 90,000 pounds inch, and I is a moment of inertia of the whole entire cross section. So that is given by this formula here. So we calculate it. And what is Y? And if we want to determine the maximum value of the normal stress, we better to find the Y, that is the maximum. And what is Y? Y means the distance between the point you're interested in the bending moment. That is the distance from that point to the neutral axis. So from this case, you can see the maximum stress is here, either here or here. And here, actually, this is in compression, this is in tension. So basically, from here, you can see Y simply equal to C over Y equal to half of the height. So Y equal to C, okay, equal to D over 2 here. Okay, so Y we determine here. So plug in all the information, basically you can lead to so those information here. And in this calculation, the D will be parameters. So from their case, you should be able to find this one. And now the next one, we focus on the determine the tau, and tau equal to VQ over IT. And also earlier in the previous slides, if you remember, for rectangular cross-section beam, the maximum is this one. So I directly pick up that value here. Okay, so the maximum shearing stress is given to these equations and less than this one. So from here, A equal to BD is a function of D. Okay, we're looking for the dimension of D here. So from here, you can find that D is greater than this. So have the value of D to satisfy this equation and this, this requirement and this requirement. So D must be minimally must be greater than this one. So that is our required. Okay. For this example here, and again, this is the beam, and under the loading like this. Basically, this is the pure bending. This is the very first example we learned in chapter 4, pure bending. Okay, and this is the I-shaped beam. And here for this example, I want to know what is the shear stress here, what is the shear stress here. Okay, so again, to determine the shear stress, we know that tau equal to VQ and over IT. So the first step, we need to determine what is V and what is I. Okay, and then of course the remaining T and T, that one we can still deal with this one here. So the first step is I want to determine V. So either you can take the sheared and bending moment diagram, but here since I take another route, I simply pick here is an AN here. Okay. So AN here, I simply take the free bar diagram. So simply I take the free bar diagram. This is a free bar diagram I pick here. Okay. So from taking this free bar diagram directly, I can see the V equal to 1.5 kilonewton. So here, let me translate. So this is the V here. Okay. So basically here the V I picking up is from this side view. This V is like this. Okay. So again, if you want to see in 3-dimensional, so the 3-dimensional model will be like this. Okay. So this is the end A here. Okay, so that is, hopefully you see, so that corresponding to the end A here, and there we have a support at the end A here. Okay, so that is a V. So once we determine the V, and then we can then the next one is determine the I. Okay, so for this I think this I kind of skip the determine the calculations, but here I provide the I here. Okay, so again, this number I think you should be able to refer to the chapter 4. I think that's the typical examples there. So we have the I. So again, tau equal to VQ over IT. And from here, we have determined the V, and which is the 1.5 kilonewtons. And we have determined I, and for example, I here, I've been calculated for you. So now we need to determine the Q and T here. So for example, we're interested the shear stress at here. So for this case, I pick this shaded area for Q. Okay. So then we call this is a QA. So this is QA. So QA basically is the area, and area equal to this, and multiply with the centroid to the neutral axis. So this is our neutral axis here. Okay, and you can refer to the detailed information here. So this is the distance provided here. Okay. So then T, what is T? T is the width, and the width is here is the 20 millimeter here. Okay, so T. So that's at point A here. So now we can see at point B here, along the BB here. So for this case, we choose this as the shaded area for calculations. So for this case, the Q shaded like this one. This is the area. Okay. And then this is the centroid, and you measure from the centroid to the neutral axis, and that is the distance given here. Okay, and then T, again, T is the width, and that is the same as A. So basically T you have determined. So by using the two different calculation of the Q and T, you can very naturally determine the average shear stress. Okay.